believe in yourself, for that's the place to start. And I say, hey, hey, what a wonderful kind of day, if we can learn to work.
Okay, here we go, another quick video, and we're going to try to explain the difference between measurement in a classical system and a quantum system, right? We're going to shoot for 5 minutes here, right? So, in fact, this one's actually, I think, even easier than all the other ones. So, let's think about what does it mean to have a measurement? Well, first and foremost, something that doesn't happen when you think about it from a classical picture, but needs to be truly understood, is that measurement disturbs the system. Now, you may think to yourself, well, of course, measurement has to disturb the system, right? How else can you measure a change in state of the system if you don't disturb the system, right? But in the classical world, we take advantage of two things that help our calculations or help our scientific protocol, right? The first one is sure, we acknowledge that measurement affects the system, it disturbs the system, but we assume that the measurement device or the measurement plane really doesn't change the state of the system, right? So the way I like to think about this is think about a thermometer and put it in a pool, right? Of course, the thermometer is going to affect the temperature of the pool a bit, or so slightly, right? But the thermometer is so small compared to the huge volume of the pool that the temperature effect on the whole system is so small that we don't even need to consider it. The measurement that the reading that the thermometer gives off is an accurate temperature of the pool, right? So we say that that measurement is negligible, right? And excuse my pronunciation, I'm not a very good English speaker at times, right? So that's one way we say measurement happens in the classical world, right? We say, yeah, it affects the system, but uh, it doesn't matter, right? It's such a small disturbance that it doesn't really affect the system, right? The second one is you acknowledge the fact again that measurement does affect the system, and you even acknowledge that it can be violent, right? So you can think about like a chemical reaction, right? So you put two chemicals together, and there's like entropy, there's exothermic, endothermic, whatever chemists talk about nowadays, right? And so there's a very, very violent reaction, a lot of things happening, but we can account for it. We say, okay, if I mix these two chemicals together, I expect this reactant to occur, and I expect this result to come out, right? And the result is us taking advantage of the fact that we can predict exactly how measurement or how our chemicals affect each other, right? So that is a measurement process, right? We say, mixing these two chemicals, I should get this result. You're taking into account that the chemicals are going to react in such a way all predictable, and you get the end result out. It's the world of chemistry. It works, right? It's saying, okay, cool. I know these things are going to have such a huge violent reaction. It's going to disturb the system in such a way that I can predict every step of the way what's happening, and I can get the exact result I need at the end. Boom, perfect. However, in the quantum world, that's not true. In the quantum world, what happens is you start dealing with these things called quanta. And the quanta is so small that any type of interaction that happens with it disturbs the system beyond belief. And it's very interesting in the quantum world. So the first thing that occurs is that first type of measurement goes out the window, right? When you're dealing with an electron, you're just dealing with an electron, right? So we're not talking about a huge body of pool here. We're talking about one of the smallest objects in the universe. And so if you can interact with one of the smallest objects in the universe, well, hey, guess what? That object is going to be reacting very violently. So we can't say it does not disturb the system, right? Or we can brush it underneath the rug like we do with the thermometer in the pool. And on the second account, that's what we learned before, is the unfortunate reality. Quantum mechanics is truly random. We can't actually predict how our measurement is going to affect the system. It's truly random. So That is the two differences between a classical measurement and a quantum measurement. In the classical measurement, we have two ways we really think about measuring, right? Yes, I acknowledge it disturbs the system, but hey, it's too small to actually make a real difference in the actual system, right? The second way is you got me. You got me. It does affect the system. It's very violent. Hey, nothing off of me. I can predict what's going to happen every step of the way, and even do one better. I can predict exactly what product I'm going to get at the end. None of those apply in the quantum world, right? Fundamentally, your system is disturbed. You have a change in your state, complete change in your state. Measurement disturbs the system completely. In quantum mechanics, we call this a projection, right? So you have some initial state. So let's say, my favorite is electron spin. So let's say I have spin up, right? Do, 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 do. I go to a different axis, I measure it. It's so violent, it disturbs the system completely. Information is dropped, in my opinion, um, and your system is disturbed. So there you go. That is, in essence, the difference between a quantum measurement and a classical measurement. One is not predictable at all. You can't apply your classical reasoning of measurements to these quantum systems because it just doesn't work anymore.